Hello everyone, my name is Isa Nosa, and today I am presenting a deep dive into the NDSS 2025 paper titled Cascading Spy Sheets. This research explores a fundamental vulnerability in web privacy, specifically challenging the long held belief that disabling JavaScript is enough to stop you from being tracked. Let's start with the motivation. For years, privacy conscious users and even security experts have relied on the simple assumption that if they block JavaScript, they block the tracking. This is why tools like the Tor browser offer safer modes that disable scripts, and why secure email clients like Thunderbird block them by default. However, this paper proves that that assumption is wrong. The reality is that modern CSS has evolved. It is no longer just a tool for making things look pretty. It has become an engine capable of leaking data all on its own, without a single line of script. This is the threat model that the paper explored. Unlike traditional fingerprinting, the attacker here cannot run code. First, the victim downloads an HTML page or opens an email. Crucially, no JavaScript is executed. However, the browser's rendering engine still has to process the CSS to display the page. The attacker constructs the CSS as a series of logic puzzles. If a specific condition is met, for example, is the user running Windows? The CSS triggers a web request to load a specific background image. That request is the leak. The attacker sees which image was requested and instantly knows the answer to the puzzle. So you would ask, how exactly does the style and language act like a spy? Let's look at the mechanics. The authors exploit three modern features that effectively turn CSS into a logic engine. 1. Container queries. These are the big game changers. They allow CSS to act like an if statement based on the size of an element. 2. Mathematical functions. CSS can now perform complex math like calc, min, and mode. And 3. Selector logic. We can build complex logic gates using selectors like has and not. Together, these features allow the attacker to write a program entirely in CSS. The first technique is font fingerprinting, which acts like a digital ruler. Here is the intuition. Different OS, like Windows versus Mac OS, render the exact same font at slightly different widths due to difference in anti-aliasing and smoothing. The attacker creates a hidden container with a specific string of text. They then use a container query that is the code you see on the right. It basically says that if this text is wider than 100 pixel, load leak.png. If the server receives a request for leak.png, they know that you're on OS that renders that font widely. By chaining all of these checks, they can fingerprint your OS with high precision. The second technique is even more subtle: arithmetic quirks. It turns out that browsers on different operating systems handle floating point math differently at a very low level. If we ask CSS to calculate 10 pixels divided by 3, a Windows machine might round it up to 3.33 pixels, and a Linux machine might keep much higher precision at 3.3333 pixels. By writing a CSS rule that triggers only on the exact rounding value, the attacker can leak your underlying hardware architecture. Those are the theories. Now I want to show you exactly how this works in the live environment. To demonstrate this vulnerability, I set up an environment that proves that CSS is responsible for the data leakage. So let me walk you through the exact architecture of this demo. I am running a split screen setup. On the left side, I have terminal connections to a virtual machine. This represents the attacker server and the hosted environment. And on the right side, I have the victim's browser, which is a standard Microsoft Edge instance. First, let's look at the network. In the top terminal, I established an SSH tunnel. This forwards port 8000 from the remote VM directly to my local machine. And this is crucial because it allows my local browser to access the malicious page as if it were hosted locally, while the files are captured remotely. In the top left terminal, I navigated to my CSS demo directory and I launched a Python web server. This simple command turns the VM into the attacker's listening port. Any request made by the victim, like fetching an image, will appear here in these logs in real time. For actual exploit files, I created four specific files for this proof of concept. First, the index.html file. This is the bait. It's a minimal HTML shell that links to our style sheet. Second, I created two image files, a.png and b.png. These are 1 by 1 pixel images. They act as our signals. If the server sees a request for A, it means one thing, and if it sees for B, it means another thing. So finally, the main part of the attack, style.css. I have opened style.css in the bottom left terminal using the nano editor. For the logic, I define the class called .container with a specific width. Then I use CSS container query that at container rule that you see. It acts as a logic gate. It says if the container width is greater than 600 pixels, load image A, and otherwise load image B. And now moving over to the victim's browser on the right. To verify that this is truly a scriptless attack, I opened Edge DevTools using Control Shift and I. I then used the command palette and then I type disable JavaScript. Right now you can see that the warning icon confirming that JavaScript is completely blocked. Then I also went to the network tab and I checked disable cache and also preserve log. This ensures that the browser doesn't hide any requests from us. We want to see every single packet leaving the client. So now when I load the page, you see a red bar. If you look at the network bar, you can see a request for b.png. And if you look at the Python logs on the left, you can confirm that the server received get/b.png. This tells the attacker that the container is smaller than 600 pixel threshold. In a real attack, this would indicate a specific OS font rendering width. Now, let's simulate a victim with a different configuration. Let's say a Linux user where fonts render wider. Now going back to my nano editor in the bottom left, I am editing the width property of the container. I'll be changing it from 520 pixels to 700 pixels. This change is purely CSS. I'm not touching any HTML or script. So now I hit Ctrl O to write the file, Enter to save, and Ctrl X to exit the editor. Now going back to Edge, I am performing a hard reload to force a fresh fetch of the style sheet. And now let's watch what happens. The bar instantly flips from red to green. Because the width is now 700 pixels, the container query condition, where width is greater than 600 pixels, has evaluated to true. Consequently, the CSS engine fired a new request. If you look at the network tab, you would see a.png. And if you look at the attacker's logs in the top left, you would see get/a.png has appeared. We have now successfully exfiltrated data from the client to the server. We changed the client server property and the CSS logic detected it. And it signaled the server by requesting a specific resource. And we did all of this with JavaScript disabled, which proves that the browser's rendering engine alone is enough to compromise privacy. That demo showed a single check, but when the authors scaled this up, the results were staggering. They tested this on over 1,000 browser and operating system combinations. They achieved 97.95% accuracy in uniquely identifying the pair. Perhaps more concerning is the email client vulnerability. They found out that 8 out of 21 tested email clients were vulnerable. This includes major secure clients like Thunderbird and iCloud Mail. This is why the email vector is so scary. In a browser, you might expect some tracking, but in email, we expect privacy. Imagine an attacker sends you an HTML email and you don't click any links, you just open it. The CSS immediately runs a calc check on your system. If you match a specific target profile, say a Linux user, it triggers a request for a tiny invisible 1 by 1 pixel image. The attacker sees that request and then knows that you opened the email, what device you used, and that you are their target. This bypasses almost all standard email privacy protections. So, what can we do about it? Current ad blockers struggle here because these requests look like legitimate images. The authors propose architectural fixes. For browsers, they suggest preloading conditional resources. Essentially, the browser should be forced to download all possible background images referenced in the CSS, regardless of whether the if condition is true. If the attacker sees requests for everything, from Windows to Mac to Linux images, they learn nothing. the signal is destroyed. For email, we need server-side sanitization. The email provider should rewrite the CSS to resolve these variables before the email ever reaches your device. In conclusion, CSS is no longer just for styling, it is a computational attack vector. The no-script safety net is broken, and disabling JavaScript is insufficient for privacy. We really need to start treating CSS with the same security scrutiny that we give to JavaScript, and browser vendors need to adopt preloading defenses immediately. This concludes my presentation on cascading spy sheets. Thank you for your time.